Hey, welcome back. So far, we talked about LLM training using RAGs and PEFs and LoRa and stuff like that. But this week, we'll talk about something different in terms of quantization. What is quantization? How to load large language models onto small consumer grade graphics cards, or even if you don't have a graphics card, how to load it into RAM on your MacBook or stuff like that. So let's talk a little bit in terms of why it is needed, right? So if you have a H100 or A100 NVIDIA form of graphics cards, then you don't need this video. But even if your company has H100s or A100s for your production deployments, when you are developing a new product using LLMs, you don't want to waste the resources of a expensive the machine, whereas you want a dev setup where you play with your ideas and do your own training with loading the models into smaller graphics cards, and then once you have your ideas gets concrete, and then move to a expensive equipment, right? And also here we need to talk about because these are expensive, and also the deployment of these is going to how you deploy, how many you deploy also depends on how many active customers you have, right? So if you have like multiple concurrent customers coming in, you just having one H100 is also not going to be enough. So but again, before going in there, you need to know, you need to play with your hypothesis as a dev, and once your once your model is behaving the way you wanted, then you can go into much bigger hardware. So yeah, in that sense, so you want to load a given LLM, so that now there are two aspects, right? Somebody is taking care of the hosting and everything, like OpenAI, GPT-3, GPT-4 kind of a thing. You just pay money to them, and they are taking care of load balancings and stuff like that. Even your dev effort is simple there. The second one is open source side of the story, where you have llamas or mistrals, and mixtrals are open source or open weights kind of a models, right? And there is a slight difference there. Open source is including the training data, everything is available to you, whereas open weights, only you are able to infer out of these models. You can load it onto your consumer hardware and host it, but whereas the training data is not available to you. So mixtrals are example of those, right? You can still fine tune, but it is limited in terms of what training data they have to do a full fine tuning, right? So so you go into Hugging Face for these open source models, and either Phi or Llama or Mistral, you find different format files out there to download for these models. Some are like GPTQ or GGML or GGUF and AWQ. So it will be confusing if you don't know what these file types are, right? So in this video, I'll talk about including a example of how to load each of these files, and how to infer out of these. I don't go into the fine tuning right now, but it will be a lengthy video. I'll do one more video of quantized fine tuning using QLoRa and stuff like that later, right? Before that, let's jump into what is the some of these concepts and what we are talking about. So when you are talking about a model, a large language model, so first you define different layers of the neural network, and then you select your training data, and you initialize the weights to a random float, and then you start to send the data, and then send the training data, and you optimize, or to minimize the loss, you do back propagation and update the weights. That's how the model weights are going to formulate, right? So the more so you define the number of features, and you have much bigger training data, and you train it, and the more you train, more features it'll acquire in terms of parameters, is what the model is about. So the more parameters, the more capabilities it has. Bigger is always better, but comes with a cost, because while you are training a lot more data, you are also making the size of the model bigger and bigger. Okay, let's talk about that a little bit more. So in a full precision, floating point 32 is the numbers that we are talking about down here. For Bloom, or Bloom is a 176 billion parameter model. It will require 845 GB of FP32, I mean 845 GB of VRAM needed. So it translates to 11 H100s that you need to just infer this particular model, right? And you want to fine tune, you need 35 of H100s, and if you want to use LoRa and only do a subset of the layers, I mean subset of parameters to fine tune, you require 11 of the H100s or A100s for that matter. And Llama 70 billion is about you need about 4 in the full precision, and Mistral, which is a 27 GB, you require 32 GB for inference. So in a full precision, if you have a 4090 or 3090 card with 24 GB RAM, which is the best consumer grade card that you have right now, which is 24 GB, right? So you need 2 of them for inference, and 2 of them for fine tune, and 5 of them for full fine tune, right? So is there a method to this madness? Is there a way you can at least load them? Unless so let's take Mistral 7B. Unless you have 2 cards in your machine where you distribute the model into 2 different cards, it is not easy to load onto a full precision model. So luckily we have quantization. Quantization is compressing further down, reducing that floating point FP32 to FP16 or 8 or 4, right? So there is a nice paper about 8-bit matrix multiplication at scale. So what Hugging Face did is they integrated this with bits and bytes and accelerate. So you can do a configuration of a 8-bit or 4-bit, and then you can get these models further down. So if you see 8-bit or 4-bit for Bloom 176, so compare the bigger numbers down here when you are talking about H100s, sorry, 3090s, 35 of them with 30 full precision, whereas in int 8, which is 1/4 of the thing, you only need 9 of them. And furthermore, if you quantize to 4 yeah, 4-bit floating point, you only need 4 of those cards. So 176 billion parameter model can be loaded into a machine that has 4 graphics cards of 4090 or 3090. Yeah, that is amazing. And mixtrals and mistrals, right? So these can be loaded pretty easily into one consumer grade card. So let's talk about some of the terminology down here. So we are talking about when you talk about quantization, we are also talking about sharding, normalization, quantization, dequantization. So what exactly are these? Sharding is, so let's say you have a 10 GB model, and loading 10 GB model at once is little bit of a taxing in terms of your RAM or VRAM, right? So if you have a smaller chunks, like 2 GB chunks, it is much easier to load. And also this will hugely benefit if you have multi GPU setup where you are distributing the model. You don't need to load the whole thing and then distribute. Whereas if you have a smaller chunks, you can load and then you distribute onto different GPUs. So this chunking of a larger LLM into smaller chunks is called sharding. And what is normalization? So the intake paper we talked about, what they do is they load the model, they normalize the data using a quantization constant, whether it is a 16-bit, 8-bit, or 4-bit, and then they do the quantization. So first they normalize, and then they replace the linear layers with the 8-bit or 4-bit linear layers, so that it will dramatically reduce the size of the model, right? And so this is compressing further down of the trained weights, right? So the floating point 32 coming down to the 8-bit means you are losing some precision. Yes, you will have some impact of accuracy because of loss of precision. But the goal of all of these techniques is to minimize that loss, so that your model behaves reasonably okay for your dev effort. Obviously, this is not for a production grade effort. This is okay for a dev grade effort, where you can load the model in a smaller GPU and also train and establish your idea is working, and then move on to a bigger setup, right? The dequantization. So even though you are quantizing back to the 4-bit, when you are inferring, the model can, based on your configuration, the model can infer in dequantize to 32-bit or 16-bit, and do the inferring, so that accuracy is a little bit more than doing it on 4-bit. And also the graphics cards are much more efficient in 32-bit floating point numbers, because they are 32 and 16-bit, because those are natively supported. So your efficiency, the token rate will also increase if you do that way, right? So there are different quantization techniques like bits and bytes, and GPTQ, GGUF, and AWQ. So bits and bytes is an integration of the 8-bit paper that we saw before. What Hugging Face did is they created a library called Accelerate, which will take care of heavy lifting in terms of how to distribute the models into multi GPU side of the story, and also integrated the quantization. While loading itself, you can specify what quantization you want for that model, and it will load right away using bits and bytes. So we'll talk about that. And then GPTQ and AWQ are for GPU based quantization, whereas if you don't have any GPU, or you have very minimal GPU, you should probably go for GGUF, where it is mostly onto the CPU based inferring and training, right? So let's start with let me clear the output. Let me start with bits and bytes. So let me install first torch, and check the torch version. So we are 212 torch and CUDA 121 12.1, right? That's where we are. And for this we need transformers, bits and bytes, and accelerate, like we talked about before. And load that up. I'll share this notebook in my GitHub, so you can play around with this. So this is the bits and byte configuration. So we are saying load it in 4-bit and use this normalized floating point 4-bit notation to store the data. Like we talked about, compute D type is BF float 16, whereas when you are inferring or training, use this format, right? And there is this double quantize. So there is a nested quantization. So you will gain 0.4 bits overall per parameter with this approach. So it will help a little bit more in terms of quantization. So for this, we are talking about, we are using the Mistral 7B, which is I think 28 GB model. And my system has 3090 graphics card, which is 24 GB graphics card. So with this quantization, I can load this into. Actually, I can load even 16 FP16 type of model or 8-bit model, just for showcasing this capability, and I'm just using this. So using the Hugging Face auto model, you load from pre-trained this model, Mistral AI, and the quantization config is the 4-bit configuration to load, right? Let me run these two. So these are the shards we are talking about. So if you have a bigger shard size, you can actually reduce it, chunk it down, so that it will be easier for it to load, right? And then I wrote a helper script to get the tokenizer, again auto tokenizer, from getting from the same model. And then just to make it interesting, I'm asking for a recipe of a Indian breakfast called upma, and if you are a fan of upma, you will benefit from this also. So the model should give you the detailed instructions of how to cook upma for your breakfast. Okay, so now we are using the helper script to get tokenizer, and because this is in a format of a prompt template, so you need to apply the tokenizer prompt template. So I'll show you how it. So this differs from model to model. So that's why having something like this coming from the tokenizer is much more easier. So this model, because it's the instruct model, requires in this particular format. If other format, if you are loading Llama 70B, it has a different format, because you are loading that tokenizer. It knows how to apply the chat template for that, right? And another helper script I wrote to generate using Hugging Face pipeline. So Hugging Face pipeline is much simpler and easier to use. So I'm using that to generate out of the Mistral 7B. So this should roughly take about 30 seconds because this is not an optimized model out of the box. So you are taking a direct model and you are loading with a quantization config, whereas the other approaches are they're already quantized, so it will much easier to load. Yeah, so we got the output. So Upma is a popular South Indian dish, and he gave all the ingredients that are needed, and also gave the instructions, and it also using a pressure cooker. Nice. So let's move on to GPTQ. GPTQ is mostly for GPT based systems. I mean GPU based systems. So again, this particular guy, the block, I don't know whether I'm pronouncing it right. He quantizes and keeps different quantized models out there, so that you don't need to quantize. If you want, you can quantize. It is a time taking process, but you can definitely do it. And if you want to do it, there is a lot of documentation in Hugging Face on how to do that. So here I'm using one of those the GPTQ models. So for this, we need auto GPTQ. So, and also the auto GPTQ works along with the QDNN. So that's why we are loading those together. And also transformers, I think 37 or above is needed. So that's why I'm loading those specifically for this. Take like a few seconds. Okay, now similar thing. You are loading from the pre-trained whatever the model name, and revision main. So if you see, there are multiple revisions within the model from the repo from for the block guy. So I'm taking from the main. So now it is loading the model, and also a minute, getting the tokenizer like we did before. Again, Opma. So again, this is the prompt empty. So because the the prompt templates, the model that we are loading is slightly different from the transformers different way. So that's why I again duplicated this. Otherwise, I would have used that code from there itself. And I'm using the same generate to generate from the GPTQ. Should take about 10 seconds roughly. Let's see. 18 seconds. Okay. So GPTQ model is working good. So at this time, it is a good idea to restart, but let's see if without restart, if it works just by clearing the cache. So GGUF, there are two ways to load the models. One is called a C transformer or llama.cpp. So C transformer is a little bit behind in terms of updates. For models like Mistral and all, they are not up to date. So that's why I am using llama CPP. This is this particular GGF is for CPU based inferring, whereas but there are some layers you can offload it to GPU also for inference speed and stuff like that. So this is the command to load llama.cpp with CUDA 12 enabled. So you have to do that first, and then on your local machine on this particular VM, and then you can use it. So I'm loading llama. The llama index is so here we are saying how many layers to offload to GPU, and this is the GGUF format that we are loading. And again, so the prompt template is slightly different. We are giving a little bit more instructions. Tell me a recipe for upma. Give the detailed list of ingredients and detailed instructions. Right? We are converting the whole thing into and getting the inference out of the model. Okay, we got that. Okay, the same thing. So we got how to make upma, right? So why I'm showing all this? So let me complete the last one and we'll talk. So AWQ is also another approach. So for AWQ, we need to load. We'll be using VLLM. There is also a way to load it using AWQ interface of Hugging Face, but I felt this is much easier. So we are loading the model in AWQ 4-bit in half precision. D-type is half precision because the inference will be done in half precision, and GPU memory utilization is 0.9%. Like I said, AWQ is also GPU based approach. Okay, and then same thing, give the recipe for upma and generating. Cool. So with this, we got all three formats, major formats, and also loading the actual model also directly. So this will be useful because though it looks so simple, when you are start loading, you will playing with each of these types. There are quirks that you need to play around to make it work. So hopefully this notebook will help you either in loading it in CPU or GPU, and that's it. Thank you.